Let's look at some basic polynomials. The most basic polynomial you can have and have a y value would actually be this graph. I don't know if you can even see it. This is f of x equals 0. F of x equals 0 is simply a horizontal line going through the 0 on the y, and in this case I've changed the x-axis to purple because it is the x-axis. A slight variation on this would be like f of x equals 3, which would be a horizontal line going through the 3 on the y-axis. Here is y equals 0. This one would be y equals 3. This is a constant function because there's no variable. They're both constant functions. That is, the constant function is a horizontal line. So if we looked at y equals 1, it's just a horizontal line going through the 1. Y equals -2 would be a horizontal line going through the -2. And of course, it could be written as f of x equals -2. What about the function y equals x, or f of x equals x? This is called the identity function. It's called the identity function because the x and y are exactly the same. So it's got the point 0, 0, 1, 1, 2, 2, and so on. Now, by making some changes to the stretching or shrinking, by multiplying the x and making changes to the vertical translation, that's where you get your y equals mx plus b. So this is also a linear function. This is the most basic linear function. What about y equals x squared? This, of course, is a quadratic function, second degree. Linear function is a first degree. All quadratic functions are going to have this shape, which is a parabola. Well, I don't know how much experience you've had with graphing higher degree problems. What if we looked at an x cubed? Now, an x cubed, a cubic function, y equals x cubed. Notice that this would have the points 0 cubed is 0, 1 cubed is 1, -1 cubed is -1. So that looks kind of like it's going to be a line if you just line those up. But if you had 1/2 cubed, you get 1/8. So that's why this is actually flatter in here. And of course, if you had 2 cubed, you get 8, which is going to be way up here off in the ceiling somewhere. So notice this looks a little like a parabola that's been broken in the middle with the left side twisted down. But it's not quite a perfect parabola because cubing, after you get past the 1, makes it rise up sharper. But between the 0 and the 1, it actually kind of flattens it out a little bit. And then the same happens on the negative side. So this is going to go up forever down here, down forever. What would we see if we looked at an x to the 4th? Well, gee, that looks like a lot like a parabola, right? So here's y equals x to the fourth. Once again, when you get past the 1, the values increase even faster than they would with a parabola or even a cube. Between 0 and 1, they increase slower. So this would be flatter, this would be sharper, and of course, negatives are going to give you positive y values. What about an x to the fifth? Well, that looks like a cube, right? What about x to the sixth? Another parabola. X to the seventh? Another cube. Flatter in the middle, sharper at the ends. Let's look at a cube and a fifth and all of the odd exponents at the same time. Now with a line, it's just flat. And then with a cube, it starts to curve. And x to the fifth is flatter in the center and sharper at the ends. Notice that in every case, we've got all of them going off in this direction as we write x approaches infinity. And then it goes off this way as x approaches negative infinity. So as your x's go that way, your y's go down. As your x's go this way, your y's go up. We'll learn more about this when we look at the effects the leading coefficient has. But if you had, for instance, y equals a negative x cubed, you're going to find that the negative causes it to reflect around the x-axis. So with a negative x cubed, you're going to get something along this line. I could put the actual graph on there, couldn't I? But notice that if your exponent is odd, the ends of the graph go in opposite directions. Interesting. What if we look at the graphs of the ones that have even exponents? So we've got an x squared, x to the fourth, x to the sixth. Although when you get above the x squared, they're not actually called parabolas. They certainly resemble a parabola, right? An important thing to notice here is that if your exponent is even, as x approaches infinity, positive infinity, as it gets bigger and bigger and bigger, so do your y values. Now, this was the same with the cubes. However, if your exponent is an even number, then as your x's get smaller and smaller, as x approaches negative infinity, your y values are still going to get bigger and bigger. So as x approaches infinity, your y approaches infinity. And as x approaches negative infinity, your y approaches positive infinity. This is the main difference between an odd exponent and an even exponent. Now, if we graph x equals a negative x squared, let me put that on here. If I put the graph of y equals a negative x squared in here, what happens? When your leading coefficient is a negative, and you've got an even exponent. Then instead of both directions going up, then both of your y values going to, as x approaches infinity or negative infinity, your y values are going to go to negative infinity, but they will go the same direction regardless. So if your exponent is even, both ends in the graph go not necessarily up, but go in the same direction.